So in this video we're going to verify that 4 points in 3 space form a parallelogram, and then we're going to use the cross product to find the area of that parallelogram. So it says verify the given points form a parallelogram and then find its area. So the idea is if they do form a parallelogram, let's suppose they do. So here's the point A, which is 0, 3, 2. And then it goes up to some point B, A, B, C, D. So B is the point 1, 5, 5. And then we go over to point C. And C is the point 6, 9, 5. And then we go back down to the point D. D is the point 5, 7, 2. And then we connect A and D up. So if we have a parallelogram, the idea is that the vector from A to B and D to C would need to be the same length and parallel. So in other words, the same vector, and the vector from B to C and A to D would need to be the same vector so that they're parallel and have the same length. So verifying that the given points form a parallelogram, one way to do it is just to calculate the vector from A to B and D to C and verify that they're the same vector, so that means they have the same length and they're parallel. And then do the same thing for AC and AD. So if we calculate the vector from A to B, that's going to equal, it's going to be x component minus x component, so 1 minus 0, comma, y component minus y component, so 5 minus 3, and then z component minus z component, so 5 minus 2. And this is going to give us the vector 1, 2, 3. And then we'll just calculate the vector from D to C to verify that they're the same vector. So the vector from D to C is going to be 6 minus 5. Remember, it's terminal minus initial. So 6 minus 5. 9 minus 7. And then 5 minus 2. And then we simplify this. We're going to get a 1, 2, 3. And because the two vectors are the same, they have the same length, and they are parallel. And then we want to confirm it for the other two vectors. So we look at the vector from B to C. And the vector from B to C is going to be x minus x, so 6 minus 1. It's going to be y minus y, so 9 minus 5. And then z component minus z component, so 5 minus 5. Which simplifies to 6 minus 1 is 5, 9 minus 5 is 4, 5 minus 5 is 0. And that was the vector from B to C. Now we do A to D. And the vector from A to D is going to be 5 minus 0, 7 minus 3, and 2 minus 2. Which simplifies to 5, 4, 0. So the vectors BC and AD are the same, which means they have the same length and they're parallel. So we know that they form a parallelogram. And you could actually go into GeoGebra if you wanted to. Under the View menu in GeoGebra, there's a 3D graphing window that you can open up, and you can actually plot these points in three-dimensional space if it helps you to visualize. And then what we want to remember is we had a property, a geometric property of cross products that says, hey, if you have a parallelogram formed by vectors u and v, then the size of the cross product of u and v is the area of the parallelogram formed by u and v. So using that result from the geometric properties of cross products, that was property 5. The size of the cross product gives you the area of the parallelogram. So we use property 5 to say, hey, if I know the vector from A to B and A to D, the size of that cross product will give me the area of that parallelogram. So I just go and say, hey, I'm going to calculate the cross product AB cross AD. And then once I find that cross product, I'm going to find the size of the cross product, which will be the area of the parallelogram. So we just go ahead and do the calculation. IJK and AB is the vector 1, 2, 3. AD is the vector 5, 4, 0. And then we just grind this out. It's going to be I times, we would cross row 1, column 1, and take the determinant of this 2 by 2. So it's going to be 2 times, its determinant would be 2 times 0 is 0, minus 3 times 4 is 12. So we'd get a minus 12 sitting here. Minus J times the determinant cross row 1, column 2. And we would take the determinant of 1, 5, 3, 0. So 1 times 0 minus 3 times 5 is a negative 15. And then it'd be plus K times. And then we would do cross row 1, column 3. We would take the determinant of this little 2 by 2 matrix that's left. So 1 times 4 minus 2 times 5. We get 4 minus 10. And 4 minus 10 is going to be a negative 6. So that's going to wind up giving us the vector. I'm just double checking and making sure I plugged everything in right. It looks good. So I'm going to go ahead and, if in component form, this would give me the vector negative 12, comma, negative negative would be positive. We get a 15, and then a negative 6. So that'd be in component form. And then if I look at this, it looks like 3 shows up in all 3 of these. So I could actually factor out, if let's say I factor out a negative 3. I'll just factor a 3 out. We'll leave the rest in. So that'll give me a negative 4, and then 5, and then negative 2. And this is the cross product, and now I just need to know the size of the cross product. So the size of the cross product, the size of AB cross AD is just going to be 3 times the size of the vector. So the size of the vector is going to be the sum of the squares of the vector components. Sum of the squares of the vector components. So we get 3 times the square root of some stuff in here. We get what? 16 plus 25 plus 4. And 25 and 16, that's 31, 41, no, 2, 3, yeah, 41 plus 4 is a 45, so we get 3 root 45. And then we want to look at this and say, is it in simplified radical form or not? So what is 9 times 5 is 45. So if we rewrite this as a 9 times 5, we would wind up getting the square root of 3 coming out. So we get 3 times 3 is 9 times the square root of 5 in simplified form. So the area of the parallelogram is going to be 9 square root of 5 square units. So units squared, we don't know what units we're measuring in.